Okay, thanks, Mike, for the intro. I will be moving along and getting us started with our first session of the day, building an antibody panel. So a brief overview of the 3 talks that we're going to have in this session. The first will be from Alea, dealing with panel construction. So this really goes into sort of the trade-off that you have to make, given that you only have a fixed number of targets. How do you decide sort of what belongs and what doesn't? And what's the thought process behind how those decisions happen? Second talk will be on antibody validation. So this is once you've decided, what's going to be in the panel, how do you actually QC that these markers are working as expected? Antibodies are in the right hands, very useful, but they require a little bit of expert insight to really figure out which of them are working, which of them are not, and that ends up taking, I would say, a large amount of our time is actually doing an XQC. And then, inevitably, it doesn't always work. So Ben will be rounding out the session telling us what to do when things fail, and sort of what our process looks like for trying to rescue these targets that we have high hopes for. So, really, the goal of this session is to give some insight into what our workflow for testing and optimization is prior to acquiring a large amount of data. So this is all of the sort of homework that has to happen before you can go out and generate large data sets. The workshop in general, but specific to the 2 sessions today, are going to kind of be framed from the perspective of 2 cohorts that we are currently assembling in the lab. And so I just wanted to give a brief overview of these 2 projects because they're going to be touched on multiple times in the following session to give you an idea of what the motivation is. So the first is a project centering on glioblastoma multiforme, known as GBM. This is a brain tumor that is really, really deadly. There's not a lot of great treatment options. And Ben and Hadeesha have really been spearheading a great project in collaboration with many other people looking at this disease to gain better insights into what's going on. This is a large cohort with hundreds of patients that have been treated with a range of different immunotherapies. And the goal is to basically assemble an antibody imaging panel so we can spatially profile the tumor microenvironment within the brain to understand sort of what are the drivers of the differential response between patients across different patient groups within specific types of immunotherapies to better understand what works and what doesn't for the patient. The second project that you'll be hearing about today is a tuberculosis project. Tuberculosis is an infectious disease that is one of the leading killers in the world. It is really deadly and it is difficult to treat. Treatment regime is really brutal. There's sort of been analogized to chemotherapy for how toxic it can be to patients. And so there's sort of 2 parallel prongs that we're coming at this from. The first is with a cohort of non-human primates, so monkeys, which give really great experimental traction into understanding this disease in a way that other models historically have not. This is going to be paired with a cohort of clinical samples, and this is a project that's being led by Alea and Aaron in our lab. The goal here, similarly, is to assemble a large, diverse cohort of both animal models and patients to better understand sort of the trajectory of the disease over time, and then put that on the MIBI with, in addition, other spatial assays that are sort of coming down the pipeline to better understand how the microenvironment there mediates infection. So with that, I will turn it over to Alea for our first talk.
Hi, I'm Alea, and today I'm going to be discussing how to construct a panel for MIBI or other spatial imaging techniques. So just a brief overview of the outline. First, I'm going to emphasize the importance of a well thought out MIBI panel. Then I'm going to go into our lab's framework, which primarily consists of having a core panel of markers and then having the project specific markers for your specific study. Then next, I'm going to discuss when you should look for new targets. And then lastly, I want to emphasize when to watch for redundant markers. So just a brief overview of our MIBI pipeline. We first usually start by constructing our panel, and then we go into immunohistochemistry validation, and then to MIBI titrations. However, this a pretty iterative process. And so eventually, once you go through the cycle a few times and then confirm your panel, this validation process will be discussed in the next parts of our session. But then once this is validated, you can then go ahead and stain an image on the instrument. And then you can go through the level processing pipeline and data analysis that will also be discussed later on in the workshop. And then eventually you can publish your manuscript. However, at this stage, when you stain an image to your cohort, it's too late to change the panel. And so that's why it's really important to think carefully about what is in your panel during that initial validation stage. So now going into our lab's framework, we first like to ask ourselves, what types of cells and major subsets do you want to delineate in your study? Next, you want to consider what possible functional states are present in these subsets that you want to stratify. And so, as I mentioned earlier, in our framework, we like to consider having a core panel, which first consists of major lineage markers to delineate major immune and non-immune cell types, such as T cells, B cells, macrophages, as well as myofibroblasts and endothelial cells. And below each of the immune cells and other cells, we have listed some of our common markers that we like to use to delineate these cell types, as well as I've included some representative images that we've taken on MIBI to demonstrate these markers, such as CD3 for T cells, CD20 for B cells, calprotectin for neutrophils, etc. Next, in this core panel, we include markers for segmentation, and so this will be discussed in depth in session 5. But for segmentation, it is necessary to include a nuclear channel, which in our lab usually consists of having HH3 or dsDNA, as well as a cytoplasm or cell membrane channel that can include one or multiple of these markers, which is CD45, clementin, sodium potassium pump, or PAN-CK. And once you have these two channels, they will go into the segmentation pipeline to be able to produce a segmentation mask or of the borders that you see here in white. And then finally, that would produce our labels that we can use for single cell analyses down the road. Lastly, it's important to include some functional markers to better characterize some of the states that your cells could be at in your study. And these include, for example, IDO, which is generally indicative of immunosuppressive activity, phospho-S6 for activation, HLA-DR for class 2, granzyme for cytotoxicity, TIM3 for T cell exhaustion, T cell state, as well as KM67 for proliferation. And so these are just some of the examples that our lab tends to use in almost every single study we have. Next, of course, we want to include some of the fun stuff, some of the project-specific markers. And so these can include more specialty subsets. And in our tuberculosis project, we've included, for example, markers to indicate Tregs or gamma-delta T cells. And so here's an example granuloma from our study as an H&E. And then here's an example MIBI overlay denoting major lineage markers like CD20, CD3, CD31, and CD14 for my lymph cells. And so here I've included a inset to denote Tregs based on the expression of CD3, CD4, and FOXP3, as well as here an inset to denote gamma delta T cells based on the co-expression of CD3 and gamma delta TCR. Next, we've also included some other specific functional markers. And so here's another example granuloma with another major lineage overlay. And so in this inset, you can see the co-expression of CD3 and ICOS to denote more T cell exhaustion. We've also included some markers to look at epigenetics. And so here we can see differential expression of methylation and acetylation, which has also been shown in TNBC in addition to in tuberculosis granulomas. Next, we can also look at some cytokine signaling. And so here I've included a representative image of integrin gamma expression in the granuloma. And then lastly, we can also look at metabolism. And so here's an example of some of GLUT1 to denote glycolysis in the myeloid core of our granulomas. Thirdly, for For these project-specific markers, you can also include markers that you found based on some RNA sequencing or transcriptomic studies that your lab or others have performed. And then, of course, you can incorporate markers that you found from papers in your respective field. And so this leads into when should you add new targets? Well, our lab's recommendation is by default, you should always use markers that have been validated by others. It will save you plenty of time and money, and I can concur based on, for example, this example of just testing multiple VEGF clones. Unfortunately, none of them work. And so you might run into this issue where you have a target that you're really interested in, but nobody has validated it. And maybe for a reason, because it's just such a hard target to validate and get working on IHC or MIBI. And so once again, try and use markers that your lab has already validated, because it will save you a lot of time. In addition, when considering adding new markers, you should ask yourself, how common is the marker of interest? And so, for example, you could be looking at a marker that may be really interesting in a different tissue context, such as like CD20 for B cells. However, if you're trying to look at it at the maternal fetal interface in placenta, B cells are not very common there. You can see here there's one cell, and that was pretty surprising to us. And of course, this can happen in a lot of other contexts too. So just pick your markers carefully based on your specific project and tissue of interest. Conversely, you don't want to pick a marker that stains everything. That's not really going to provide you a lot of biological insight. And so here, for example, it's known that arginase 1 stains almost every single hepatic cell in the liver. Now, there are benefits of having markers that stain everything, specifically for segmentation, but you also don't want to have too many markers that stain everything, because once again, that's not going to give you enough biological insight. And so this leads into asking yourself, does the marker you're interested in add any new orthogonal information? And this leads into the discussion of watching for redundant markers. So when you ask yourself this question, you can consider the example of T cell memory. So for example, just some biological background, naive T cells are usually CD45RA positive, but when they're exposed to a pathogen and then undergo cell division, they end up developing a memory phenotype, which then becomes CD45RA positive. They are anti-correlative. So when defining T cell memory, do you really need both CD45RA and CD45RO to denote naive and memory T cells? This is just one example. There are plenty of others, but you can kind of think of it in this way when you're trying to figure out if you need both markers to denote one or the other. In addition, I want to emphasize that there are a limited number of match channels, and so you want to make sure each marker has a distinct purpose on your panel. And so to conclude, just really emphasizing and driving this home that there are a limited number of match channels, and so you want to make sure each marker has a distinct purpose on your panel and in your study. It is important to find a balance, so you don't want markers that aren't very present in your data set or in your tissue, but also don't stain everything. Please follow the framework that I've outlined, so which includes having a core panel that consists of major lineage markers, segmentation markers, and common functional markers. And then also you can include your project-specific markers. But following this framework will really make the downstream analysis more straightforward and will make the rest of your time analyzing the data much more useful. Okay, any questions? Thank you so much.
Okay, so our first question from the Zoomers. How do you choose when there could be multiple different markers used for the same cell type? For example, MPO, Ly6, calprotectin, like what's the thought process behind which of those you would choose for what's essentially going to be the same cell type?
Yeah, so we run into that issue specifically with this example of depending on using MPO or calprotectin. For us, we've used calprotectin just because it's a more robust marker and it has clear signal, and so we've decided to, based on those criteria, to go forward with calprotectin, for example. And so I'd say in those other situations where you're dealing with trying to decide between multiple markers, pick something that's more robust and consistent, and that you won't worry down the line may find issues.
What's the theoretical limit on the number of match channels, and what's the practical limit?
I would say practically right now it's about 40. In the lab, we're trying to expand upon that, but for now, from a practical use, it's about 40.
What's the theoretical limit? It's just like, can it just be like one extra neutron is enough to differentiate?
Yeah,
Yes.
yeah, no, I mean,
An
theoretical
extra
limit,
neutron or proton,
Yeah.
it's a new mass channel.
So you could, in theory, just have like a single stepping stone.
If you actually look at the spectra, it's like every mass unit, like especially in the lanthanide range, we have almost every single one filled up. So that the big trick is the current 40 channels are with a single chelator chemistry.
Okay.
And so I know other people are working on this. We've worked on this where the addition of different chelators allows us to add new metals in. And when Alea says practically, she knows in the back of her mind that already maybe theoretically, practically, there's already another half dozen metals floating around in the lab with new chelator chemistries that we've been using. They're just not commercially accessible yet. Cool. But certainly people could, people are playing around with this stuff all the time. Cool. Yeah.
Okay, question from the chat. When is it time to give up on validating the
When you get to 8, that's where I'm at right now with VEGF, for example. I guess it also depends on how important that marker is. So for example, VEGF was something that I was interested in and looking at the maternal fetal interface. VEGF is something that is highly expressed usually at that in that tissue, but you also want to be practical where maybe you can find something like VEGF receptor that could give you comparable information. And so I think being creative with the target of interest is also part of that. Yeah, it is hard to find a balance of like how hard to try for a target versus like not wanting to waste your time.
yeah, I think Alea's point there is important, which is that how important is the target? Because I mean, there are sledgehammer ways with really dim signals that we used in the lab. It's like you absolutely have to have something in there. If there's an antibody that works, but the staining is just really, really dim by IHC, there's ways to get around that. But I mean, the other aspect of it is that a lot of times it just becomes cost prohibitive to keep testing clones. So that's again something that I think is going to be judged by, that's actually a pretty good bar for how important it is. Are you willing to keep spending money on testing new clones?
You don't want to be spending like 3 years doing assay validation for a project that you're probably also going to spend a significant amount of time doing the data analysis for. So make it easier for yourself to shorten the window of assay validation. So then you can spend more time after the imaging and doing the data analysis.
Okay, well, we've got a lot more here, just waiting in case anyone in the room has some questions. Any suggestions for in silico validation if selecting targets from single cell RNA-seq data?
In the early processes of that,
So from what we've seen, sometimes RNA sequencing and protein level do not match. I would say I haven't personally done a lot of translating from RNA-seq to MIBI yet, but just pick markers that are extremely important in that study and then see if you can find comparable staining. But at this stage, I can't give a confident recommendation on that yet.
I would add that Protein Atlas is a great resource. So you can go Protein Atlas, go to your tissue that your RNA-seq study was done in, and look for concordance between the protein level and the RNA level. That's a good place to start. Or if the protein level staining in Protein Atlas, even though it's all kind of, some of those antibodies aren't commercially available, at least gives you an idea if someone's seen something, if the tissue localization makes sense, and whether you want to spend some time starting to chase a target like that down.
And protein atlas is also something that could be emphasized in the subsequent talks with Ben and Hadeesha.
How do you do your search for validated antibodies in the literature or companies? What's a good method?
Yeah, so our lab, this is also gonna be something that's gonna be discussed heavily in the next few talks. But we like to use some platforms like BenchSci or SiteAB to do like a bigger wide net, but we also have some trusted companies that we always go to first. And those will be discussed also further.
Okay, great. Well, there's a couple more questions, but we will, for the sake of time, move on. And I think many of these will be answered over the next couple talks because there's a lot of shared overlap. So thank you, Alea.
All right, so good morning, everybody. So I have some notes and present to you here, which is not popping up, so you might see me stumbling around, but bear with me. All right, so Leah was a great talk on putting a plan together, and I think a lot of questions kind of directed to this, to how do you actually validate these antibodies, what is the pipeline, how do you find these antibodies, and so on. So I'll be digging a little bit deeper into that part, which is really in the first part of validating or building a MIBI project, which is finding out the antibodies you want for your panel, and then how do you go about validating them. So I'll start first with how do you find these antibody clones. So, going very basic, here we all know that antibodies are these magical proteins that can bind to a very specific target. And they're so important that we have this entire class of biochemical assays, which we call immunoassays, that are designed around antibodies. Now, antibody clones are essentially antibodies that bind the same protein, but different parts of that protein. So, for example, imagine CD3. You might have a clone that works really well to bind T cells, which is what CD3 is binding or marking in cytometry, but that same clone might not work really well with Western blots. So we'll be really focusing on antibodies that bind or that work really well for IHC, because IHC sample processing for IHC is very similar to MIBI. All right, so how do you really find these clones? Well, the easiest place to start is first with IMPAC's website, because they have a lot of very well IHC and validated antibodies that have been tested to work with their chemistry. And on top of the ones that they list on the website, they have additional markers that they'll release to the audience here, or put a link to their website once the workshop is done. And these antibodies have been sort of community validated, and we know that it works, although IMPAC doesn't officially offer them as part of their catalog. Now, the other vendors that we go with, if we cannot find these antibodies with IMPAC, is Cell Signaling, Abcam, R&D, Novus, and Thermo. And we found that these vendors typically work really well with the MIBI pipeline. So how do you select the clones from these vendors? Well, the first thing you want to do is to make sure that you have a starting point, and that is to select antibody clones that are at least IHC validated. Now, just because a vendor mentions that the antibody is IHC validated, the quality of antibodies can change dramatically from vendor to vendor, clone to clone, antibody to antibody. So you want to make sure that you have some evidence to show that this antibody is working really well in IHC. So if you see a vendor, for example, claiming that this is an IHC clone, but they show you a Western blot image, probably not a great cue that this antibody is working for IHC. But there's another vendor that's showing, variety of IHC images that are across different tissues, then you probably have more confidence going in that this antibody is going to work with your IHC. Now, the other thing we do is to, sort of trust by verify kind of concept, which is you trust the vendor, but then you also want to verify it. In this case, the way that this is done, most vendors put sort of citations, whether the antibody is being used in publications on their website. So, for example, in this example, Oberlton, which has been cited over 2,100 times, you could be pretty confident that this antibody will probably work in IHC. So the last sort of consideration that we do is to make sure that the vendor can provide the antibody in a carrier protein-free version. And this is because, as you can see in this very simplified diagram, is that if there's any carrier protein in the antibody sample, when you get to the state of conjugation, which is required for MIBI, what will happen is the carrier proteins will start competing for the polymer with the antibody, and you'll end up having much lower efficiency of conjugations, and this leads to a lot of difficulty downstream. Now, if the vendor cannot offer this carrier-free version, we almost from the get-go don't even start validating it for IHC, because we know it's very difficult to purify this from the carrier protein and create a lot of downstream problems. All right, so the bottom line is prioritized testing of antibody clones that's been validated by IHC is possibly hopefully highly cited and is available in carrier-free formulation. So now that you found your antibody clones, how do you go about validating? Well, one of the important things is to make sure that you have enough positive and negative control tissues, and this becomes more and more important as more difficult the IHC is to validate. So I'm going to go through some examples here. All right, so I'll go through a few examples where some markers are very easy to validate because of certain things like CD31, for example. So CD31 is a marker that binds endothelial cells. So endothelial cells are typically found around blood vessels. So you can see that CD31 has a very specific histological site that is expressed in, as well as the type of cell that is expressed. So you have this sort of easy way to find out if you have a positive signal. Now going from CD31, when you have a marker like CD3, which is expressed on T cells. Now T cells are specific cell types, great, but T cells can be infiltrating into different tissues in very different ways. So it's very hard to find a particular histological pattern that to look for. So it becomes a little bit harder to validate CD3 compared to CD31 when you have both the specific cell type and a histological location. Now going one step harder is something like Ki67, where Ki67 is a marker for cell proliferation. So as you can imagine, many cells in your body proliferate. So Ki67 will be expressed across many cell types, but also it's not in a very specific histology. As you can see here, in colon carcinoma, almost half the cells or more than half the cells are actually Ki67. So in order to confidently validate the antibody, especially as you get away from markers like CD31, where it's very easy to validate, to something like Ki67, you want to make sure that you have enough positive and negative control tissues to really hone in on the positive signal. So you can imagine that when you have 20, 30 antibodies to validate for a MIBI panel, if you need to assemble many different types of positive and negative control tissues to validate each antibody clone, you'll end up going through a lot of time and it's quite tedious. So an easy way to speed up this workflow is to create TMAs. Now TMAs stands for tissue microarray, is where you can have different representative parts of different tissues assembled into one block, so it can go into one slide. So here are some examples of our in-house built TMAs that we use. So they're sort of divided into three different categories. We have an immune TMA, which is filled with immune-rich tissues, and that's because our lab does a lot of work with immune cells, immune cells as well as signaling pathways. So this immune TMA is what we generally use to validate those antibodies. The other one is epithelial TMA, and epithelial cells are expressed in many organs in your body. So we have a lot of antibodies that target different states of epithelial cells. So this is a great TMA to validate those antibodies. Finally, we have a cancer TMA. So we also study a lot of tumor microenvironments and proteins that are expressed there. So we use the cancer TMA to validate those antibodies. Now, sometimes even these QC TMAs are not enough, and this is what kind of happened with our tumor project, where we ended up having a lot of antibodies in the panel that were not expressed in these immune and epithelial carcinoma TMAs. And on top of that, we had a lot of mutation-specific targets, meaning that in order to validate that antibody, we need to make sure that the patient that the tissue came from had that mutation. So we had to go around hunting for the blocks that contain that mutation. So to make that easier, we went a little step further and we created our own QC-TMA to validate the epithelial tumor panel. And as you can see here, we have a variety of number of tissues, including some of the tissues that you saw in the carcinoma, the immune, and the epithelial TMA, but along with a lot of different types of glial tumors, and many of these pores contain the mutations that we're looking for. But now that this QC-TMA has been made, this can be now utilized for validating relevant markers in future panels. All right. The next thing I'll talk about a little bit is about IFC titrations. Now, a vendor will typically state a recommended titer or titer range, so that's always a good starting point. But it's almost imperative that you test more than one titer when you're validating an antibody, and that's because it becomes much easier to tell between the real signal versus background as you change the titer. So here in this example, you can see in CD86 going from 1 in 300 to 1 in 100, you see a dramatic increase in, or a dramatic difference between positive signal and the negative signal in background, as you can see here. All right, so now that you've found the clones that you're interested in, you've figured out what tissues you need to validate, and you validated these in IFC, the next step is to conjugate these antibodies with the MIBI tag. Now, I won't be going into too much detail about this because we follow IMFAT's protocol, and they have a very great protocol on their website. So I will just direct you to that. But essentially, this step is where you take your carrier-free antibody that's been validated with IFC, and you conjugate it with the MIBI tag, which contains different metals of interest. So, I'll now move into the MIBI validation and titration. Now, before I get into the titration, some of the sort of workflow considerations or tips is that at this stage, you're able to multiplex your antibodies because you're doing MIBI. So it's always a good idea to have about 5 to 10 IHC validated antibodies that you can validate on MIBI simultaneously. The next is that you should always include lineage-defining markers in this validation. And you can see that in this example, we have calprotectin, which Alea talked about, which marks neutrophils, and CD3, which marks T cells. Now, these are mutually exclusively expressed. T cells and neutrophils are very different cell types, but you can see here in this overlay that they both overlap with CD45, and CD45 is expressed on most immune cells. So this becomes really helpful when you're validating those antibodies that are expressed, or antibodies against targets that are expressed on many different cell types. Or across the tissue, and it's very hard to visually be like, hey, this is a positive signal. But I'll go through some examples that I think will become a little bit more obvious. So starting with some of the antibodies we were validating for the glial tumor project. So this one was the easy one. So this is NUN. So NUN marks for neurons in the brain. And as you can see here, it's a very distinct morphology that you see. They're not circular, they're this sort of like weird pattern of staining. And on top of that, you can almost see axons in, I'm not sure if you can see that, in neurons, or these like projectiles coming, or a single sort of tube coming out of the cell. So you have this like very distinct pattern that you're looking for to easily validate this marker. Now, when you're looking at the titer as to what is a good titer to pick, here you can see as we're increasing titer from 0.25 micrograms per mil to 1 microgram per mil, we see an increase in signal from 0.25 to 0.5, but we don't quite see an increase in signal going from 0.5 to 1 microgram. If anything, we're almost seeing a little bit more noise going from 0.5 to 1 microgram per mil. So in this case, half a microgram per mil would be a good titer to select for the win. Now moving on to a slightly more difficult target, PD-1. So PD-1 is an immune regulatory marker, which is generally expressed on T cells. But like I mentioned in the IHC, T cells don't have histological pattern or morphology that you can easily look for. So you would need further confirmation. So here, looking at just the titer, so this is an example of a dramatic difference from going from very low titer to a higher titer, but in this case, of course, it's lower microgram per mil. So 0.125 micrograms per mil, you can see, you can see signal, but it's really hard to make out the cells. But at 0.5 micrograms per mil, you can see clear membrane staining, which is what is expected of PD-1. Now, because, like I mentioned, PD-1 is expressed on T cells, and now that we are multiplexing when we're doing MIBI validation, the importance of including lineage markers is that, as you can see here, this is the highest titer of PD-1 that I showed in the previous slide, so 0.5 micrograms per mil. And you can overlay that with CD3, with T cells, and you can see this clear overlap between PD-1 signal and CD3. So now you're confident that A, you selected the right titer, and B, now the antibody is actually binding to the epitope that it's supposed to. All right, now moving on to Ki67. So this was one of the examples I gave in the IHC validation as well. So Ki67 can be expressed, again, by many different cell types, but what we can use to validate is the substituted location. So Ki67 is known to be expressed in the nucleus. So what we see here is nuclear staining. So that gives us some confidence that Ki67 is actually, or this clone against Ki67 is binding Ki67. Now focusing on the titers here, you can see here going from 0.25 microgram per mil, which is the middle one, to 0.5, we do see an increase in signal. So again, here this would be a case where I would select the higher titer at 0.5 micrograms per mil. Now keep in mind, even though I am calling these high titers, you can see that the range of titrations, like these are in the 0.125 micrograms to about 0.5 micrograms. The majority of our MIBI antibodies that we found fall within sort of the range between 0.25 micrograms to 1 microgram per mil. So another way, so this is again, because we're multiplexing here, we can make sure that Ki67 is indeed, overlapping the nuclear region by overlapping overlaying the image of dsDNA on Ki67, and you can see this sort of beautiful overlap. But another way, on top of that, to validate Ki67 is to look at the expression of Ki67 across different tissues. So this is an example of looking at 6 different tissues where Ki67 is expressed in, and on the rows you see the increasing titer. And here, as expected, in the normal brain and the liver, where you don't expect a lot of proliferation happening, you have very low Ki67 expression. So now at this point, we're really confident that this antibody is binding Ki67, it's nuclear, and it's expressed in tissues where you expect that high proliferation, especially cancers like melanoma, ovarian cancer, diffuse disease, and the tonsil, which is sort of a hotbed for proliferation. All right. So the final consideration to take into account when validating MIBI is sort of the size of the FOV. Now with IHC, you're able to sort of scan the whole image and just visually see where the marker is. But in this example, so this is a tonsil with calprotectin looking at neutrophils, and you can see if you select an FOV that is sort of in the area of where there's no signal, you will not be able to see it. And that's this, sorry, we're going back into the FOV size of the MIBI. We have a limited sort of size that we can scan for each FOV. And in MIBI, it's generally 400 by 400 microns or 800 by 800 microns. Whereas this tissue is, multiple millimeters or multiple centimeters in size. So you can see if you selected a 400 by 400 micron FOV in a region where there's no signal, you will not be getting validation on MIBI. So it's important to know how sparse your signal is in an IFC before you go into validating the target MIBI. So with that, I hope I was able to sort of convey how to find antibody clones to validate on MIBI, what the pipeline that we use to validate, and how do we go about in MIBI or using MIBI to titrate the antibody and to make sure that it's actually finding the right target. All right, with that, I will take any questions.
Hi, thank you. I was wondering if you would recommend like truly saturating the signal. So like in your example of pi 67, I would say like 0.25, you can see obvious positivity, but then are you recommending you should go up to your titration where like 1 below where you no longer see an increase in signal?
All right, so that's a really good question. We've had debates about this. So there are two types of sort of markers that you can put in your panel. It could be sort of a marker that you just want to identify a cell type where the degree of expression doesn't really matter. So that would be like, HH3 or, nuclear or segmentation ones like Romentin actually might matter. But there are markers where you don't really care about like the degree of expression within a cell. You just want it to be positive or negative. So like binomial. Anyway, and this is
Binary.
binary, that's binary expression. The second is where you want to see a difference in expression levels. So when that is the case, you want to be able to have enough antibody to saturate the signal when there's a lot of the epitopes present in that FOB. But you also don't want to keep increasing the titer to the point that you're at like sort of plateau and you're just increasing noise, but the 60 or there's a lot of free floating antibody. But then again, you also don't want to be at the lower end where if you have in a scenario a lot of epitopes, but you're not able to saturate that signal, you might not be able to see the difference between the expression of the the low expressing portions of your tissue or the high expressing portions because you're just not saturating the signal. So to that question, like we would prefer to be on sort of the higher end of that curve when it is a signal that you're looking for dynamic range. But to also make sure that you don't go above that, because there are two issues that we've run into when we're using higher titers of antibody, and that is antibodies get aggregate, which is a big issue. And we do have some methods that Ben will talk about on how to remove aggregates. But also you end up increasing more noise and it becomes much more tedious downstream to clean up the signal when you have a lot of noise, and you have more non-specific binding if you keep increasing the titer as well. And then that becomes much harder to remove computationally when it's not really like sort of background noise, but non-specific binding to the actual cell type. There's always a balance between those.
Thank you.
Hi, Hadeesha. I had two questions. You mentioned at the end the 400 versus 800 FOV. Is that just like a choice per project, or is that like when you think there might be more architecture that you care about in each of your TMA cores, or like what do you choose and why?
Yes.
We repeat the question for the.
Oh, yes. So the question is, for MIBI, you have an option of selecting a 400 by 400 micron FOV or an 800 by 800 micron FOV. And the question was, when do you select that? Is that project based? So the answer is yes, it is project based, and it depends on how much area you want to cover for each FOV and the time that you want to spend acquiring the data as well. So 400 by 400 FOV is of course 4 times smaller than the 800 by 800. So the acquisition time is 4 times faster, but it's also covering 4 times less area. The other thing is, I won't get into too many nuances here about the corners and stuff, but yeah, so I'll talk a little bit more about this in the second session where we're talking about maybe acquisition considerations. Yeah.
There's 2 questions from Zoom about antigen retrieval methods. So how do you decide what to do?
All right, so there's different kinds of antigen retrieval methods in terms of different pHs that you can use. But so when you're doing an IHC, you have the luxury of sort of deciding a different antigen retrieval method for different antibody to really optimize the signal. But with MIBI, because we're multiplexing like 40 different antibodies, you have to select antigen retrieval method or pH that works for most of the antibodies. And from what I've seen, pH 9, so the MIBI protocols have antigen retrieval working at pH 9, so that's a TRIS EDTA buffer. And this sort of works, at least from with our experience, seems to work for most antibodies. So yeah, so we would highly recommend sticking to at least one method of doing it, because if you're changing your antigen retrieval protocol, you would need to validate all your antibodies are working, including the ones that have been pre-validated by IronPad and so on.
Yeah, I'd probably even add a harder emphasis on that, which is that you should be dragged kicking and screaming into changing the epitope retrieval protocol, because as soon as you change it, you've now, if you've got a lot of reagents that you validated under that condition, you can't assume that they're going to work in the new condition. So it's like, so to the extent that you can just hold that constant, I would strongly recommend that.
What is the source of background noise in MIBI images, since there's not autofluorescence? What is sort of the salt and pepper stuff that people are seeing in the images?
So I think we will be covering that a little bit, actually a lot more in detail in the second tomorrow, I believe. But some of the images that you saw there, the noise, let me see, it could come from some non-specific binding, or it could be, I'm not probably not the best person to ask this question. I'll just end it with that, but we will cover that in more detail in the next session.
Okay, another one. How do you determine if an antibody is working or not? Is there like a ratio of signal to noise? You look at some quantitative metric, or is there another way that you determine that the antibody works?
Yes, so I think Mike likes to call this the eyeball test to make sure that it's working. You want to make sure that it's actually binding the right target. So you do that mainly with IHC, where you see, if the antibody binds the right location or the right cell type. And we really do that with MIBI, where you can overlay different lineage markers to make sure the antibody is actually binding that the marker. But when we're talking about very dim antibodies where we don't have great signal, but if the antibody is still binding to the right epitope and performing as it should, we would still include that in the panel, because it still adds information, at least in identifying cell phenotypes.
Okay, let's say you have a new batch of antibodies from an antibody clone that's already validated before. How does this workflow change?
All right, so if you have a new batch of antibody, so in our lab, we go through some basic QC steps for every antibody that comes in, which I have included here, which is to make sure that the antibody is still carrier free, that they don't accidentally include a carrier protein in there, and then then the vendor actually provides the amount of antibody that they say they did provide. Just because when you're conjugating the antibody, you need to make sure that there's a certain amount of material antibody in that reaction. And then we would not additionally validate that in IHC because we know the clone works, but we would include it into a MIBI validation prior to including it into a whole thing, because we're not sure at that point, because if we conjugated the antibody, anything that sort of went wrong during the conjugation step. And Ben will talk a little bit more about detail on things that could be going wrong within each of these steps. So you kind of get more appreciation of the validation process when you know what goes wrong in each step.
Just to kind of like Hadeesha hit on these, but like the two big things that we do is if it's already been validated and we've already seen it works well by MIBI, and we're just reordering, we run an SDS page gel to make sure that it's still carrier free. We conjugate it and then we test it by MIBI. So we jump straight to that, and then if it works, then we aliquot it out and store it.
What can cause an antibody concentration to change over time for tissues? Is it project specific, clone specific, to different masses that you label to better? What are all the things that could cause it to change?
Like once it's been conjugated, or once it's being conjugated. So this is, I guess, some of the things that we've come across personally is when you have an antibody that's been conjugated for a long time, you may end up using more titer, months down the line, just because the antibody isn't performing as well as it was when it was initially conjugated. But we're talking like, months down the line, or like a year down the line, you would want to retiter the antibody. Another reason that you might want to retiter is you're changing tissue types as well. We found that the same titer doesn't necessarily apply to across tissues. So it's always a good idea to retiter your antibody on the beat as you're changing project.
What's the shelf life of a conjugated antibody?
I'm gonna use the technical answer, which is 1 year for unpassed conjugated antibody, if I'm correct. But if you want to know more details about specific shelf life of specific antibodies, you can come talk to me during the the office hours this afternoon.
Okay, we'll do a couple more. We shortened one of the later sessions, so we can go a little bit later on this one. Are the titers between IHC and MIBI comparable? And what's the main goal of titering an antibody?
Right, so I would say it's comparable to the point that it's in the same sort of magnitude, but it's often not the same. And that's because for IHC, we have a step of secondary antibody amplification, so you get more signal and you're detecting this visually. So this is a very different detection method where you're just scanning, you're looking at the image under the optical microscope and you're looking for the color metrics change. Whereas in MIBI, you're ionizing your sample and you're measuring the secondary ions, hitting a detector in a mass spec, so very different type of sensitivity. So taking that into consideration, what we typically found is that MIBI titers are slightly higher than IHC titers, but again, going from like 0.25 micrograms per mil to maybe like 0.5 or 1 microgram per mil. So it's still within the same ballpark, but it's not identical to IHC. What was the second part of that question?
What's the goal? Like, why are you trying to find the titers in the first place?
Right. So I think we kind of answered that with the first question, which is you want to make sure two. I mean, one, you have an antibody that's just identifying a cell type, then we're not too worried about the titer. We just want to make sure we're minimizing noise and we're using as low of a titer as we can while getting positive signal. But if you want to know sort of the dynamic range of expression of that epitope that antibody is targeting, you want to make sure that you have enough antibody to bind to the epitopes when there's a lot of that present. So you want to titer that antibody so you see a lot of it. So I'm just going to give an example here. I think Ki67 is a good one. So we care about relative Ki67 expression. And you can see here almost, so this is serial sections of a tonsil tissue. You can see at the 0.25, the signal generally is dimmer than Ki67 at 0.5. So if you were to sort of analyze this downstream, your max and sort of min will be very, the dynamic range of expression would be smaller if you had selected a lower titer versus a higher titer. Now you have a much higher, high end, so your dynamic range is increasing. So when you care about the dynamic, expression of your epitopes, we should be trying to titer a little bit, enough titer for you to see that the signal isn't changing as you keep increasing titer.
What is the penetrance of antibody staining? One should do a thicker section or multiple D stacks or something like that. Like how deep into the tissue does it actually stain?
From what I understand, because you are doing an anti-retrieval state, it should stain throughout the tissue, but I've never actually gone all the way to the bottom.
Yeah, we've drilled through. I mean, it has a lot so it's going to depend on the titer. It's going to depend on how long the incubation's for, but by and large, in general, we found that if you're doing 4 micron sections and overnight incubations, you get full depth penetration. So if the sections are thicker, then I'm sure if they get, if you're doing like 50, 100 micron sections or something like that, maybe that would change. But yeah, we've seen that it pretty much goes through the whole depth.
Okay, well, we're gonna have to stop now, otherwise we'll keep Hadeesha here forever. So thank you, Hadeesha. Yeah, not too much space.
Hello, everybody. My name is Ben. I'm going to my third year grad student here in Sean's lab. I'm going to be going through a couple of troubleshooting issues or methods that we've had sort of figuring out when the antibody's not working. Just do want to preface that this is not a exhaustive list of everything that could go wrong and how to solve everything that might ever go wrong whenever testing an antibody. This is just some of the things that we found to be the most common and things that we've sort of figured out how to nail down over the last few years. If you do have a very specific issue, you know, there might be a very specific solution, but I cannot cover everything that possibly go wrong. So here, what we are going over is sort of repeating the same timeline that Alea and Hadeesha went over. What we're looking at is if we're going from that panel construction to IHC, you're finding that for some reason you saw an awesome IHC online and you got it and it didn't go right. What's happening there? If you had good IHC and it's not showing up on MIBI, what's going on there? We're bringing everything together. You got your titers and it's not working. What's going on there? So sort of just addressing a couple of these issues you might find. So we're going to do a quick overview of the issues that we'll be addressing. First and most beautiful thing that can happen is nothing goes wrong with your antibody. You get it in, the IHC works perfectly. You conjugate it, the IHC is still working, and then you put it on MIBI and you get beautiful image. And you know, this is in theory how things work every time. So you get an unconjugated IHC, and you're able to get nice staining. It's a little hard to see here, but getting pumpkin staining, which is in line with your order, and it looks exactly as you think it should. You conjugate it, and the IHC continues to look good, and then you do a MIBI image, and your MIBI image is in line with what you saw in IHC. So this is the dream of what we have happening, but there are a couple of cases where these things aren't the case. This can be a decreased signal post-conjugation. So you have an initial IHC that looks good, but you have a conjugation, and for whatever reason, after conjugating your IHC or your antibody, you're not getting the same IHC you were initially getting. And then of course, because you're not getting a good IHC, you're also not getting a good MIBI image. There can also just be a decrease in MIBI image. So you did an initial IHC, it looked good. After that, you conjugated another IHC, also looked good, but for whatever reason, your MIBI image is not showing up. Or your antibody is no longer working on MIBI. So we'll be addressing this issue. And then lastly, we'll be addressing aggregation. So this can happen sometimes as it just says you reach really high titers, or there's some antibodies that are prone to aggregation, and sort of some things that we can do to address some of these aggregation issues. So there's a couple initial assumptions because there can be issues outside of what I might be talking about. So there's a couple things that Hadeesha talked about a little bit earlier, things that we do regularly with our antibodies when we order them to make sure that these things should be working. So we want to make sure that we have PSA-free antibody in order to avoid there being conjugation interference, as Hadeesha was speaking about earlier. So as Mike had said, we do an SDS page on any antibody that comes in. So as you can see here, these are a number of antibodies that we all ordered. Christine in our lab and Mako will always do this test on all the antibodies that we order. And you can see here, there are some, the row in red is the PSA. We have a couple antibodies that did have PSA, which would interrupt our conjugation. So you want to always check for that because that can be a source of an issue. So I'm assuming that this has already been done. And then you're also doing an initial IHC test. So when you get your antibody, the antibody is working, and that you didn't go straight from ordering an antibody to conjugation in MIBI, and it's not showing that, and there was never an initial IHC done. So these are a couple things that we do in our lab ahead of time, and this might address a couple issues that might happen. And then, so from there, we'll be looking at troubleshooting any additional issues. So the first issue that we'll be looking at is post-conjugation failure. So this is when you're having some sort of initial staining that's looking good. And then after your conjugation, for whatever reason, all of your staining disappears. And so there's a couple of issues that we can have here. The first thing I'd like to say before addressing this issue is it's not very common. It's not very often that we see this difference. I think in asking around the lab, it was actually difficult to find an example of this. But I do want to mention it just in case it does show up for anybody. There can be some sort of conformational change due to the metal loading on the antibody that's having some sort of impact on the binding affinity. And this can cause a decrease in the antibody's ability to bind to its target. So our general solution here is unfortunately that we'll just try different titers. So if you're just getting minor decrease in signal, it might be an increase in titer can allow you to continue to get the signal that you're originally getting in order to offset whatever you might have lost due to the metal conjugation. But of course, always, if that didn't work, you can go and try a different clone that might not be prone to being edited due to the conjugation. So this is probably the most common issue, or like the most important issue, is sort of if your initial antibody was working and for whatever reason is now not working on MIBI. And this is sort of the process. What you would do is you have an unconjugated IHC that looked like it was working. And then after conjugation, you're still getting the antibody working. And then for whatever reason on MIBI, there's just nothing, there's no signal. And that's always a fun time for us. And so what the general cause for some of these can be is the metal was not sufficiently conjugated to the antibody. So what can happen here is due to a number of different reasons, you might have an antibody that was not able to be fully loaded with the metal of interest. So even though it is sticking to its target, when being rastered by MIBI, the metal ions are not being brought up into the machine, so you're not able to get a readout on the metal that's inside or the metal that's conjugated to the antibody. So you might also have the case that some of the antibody got conjugated, but not all of the antibody. And maybe there is some sort of conformational change that's happening that's decreasing the binding affinity of the conjugated antibody versus the unconjugated antibody. So the unconjugated antibody might be binding tighter than the unconjugated antibody is binding tighter than the conjugated antibody. And because of this, what you're getting is the unconjugated antibody is outcompeting the conjugated antibody. You're not able to, again, see the signal you'd like to be seeing. And then, of course, there's a potential that maybe you had a PSA or some sort of other protein in your sample or in your antibody. And this is what took up some of the metal when you're doing your conjugation and not the antibody itself. So with this being the case, these could be a number of reasons why you're not getting any signal on your MIBI. And the first thing that we always do whenever this is the case is we want to check to make sure that our antibody is metal loaded, and we do this using solution ICP-MS. And so we have our cytop in our lab that we'll use. Normally we'll run the antibodies through to make sure these antibodies are metal loaded. However, with our cytop, there are a number of external companies that are well trusted to send your antibody to and see if there's been metal loading on that antibody. After doing that, if you're finding that the issue is some sort of metal loading, you can try reconjugating this antibody and seeing if maybe there was some sort of issue where you found that there was protein and you were able to purify out that protein and reconjugate. And of course, lastly, if you were unable to reconjugate this antibody and get it working, you can try for so the last thing that I'd like to talk about of the issues is antibody aggregation. Again, this is not super common. However, when it does pop up, it is something that you do want to address. Hopefully you can see here, this is an antibody that we had that was aggregating. So an aggregate, you can tell sort of the difference between proper staining and an aggregate. It's very small punctate dots. It almost looks like you just put sprinkles on top of your sample, and it's just these very bright dots, and they don't look like they morphologically should when looking at an IHC. And we found that the addition of EDTA was useful in our ability to be able to remove some of these aggregates. So you can see here a sample without EDTA. And then when adding EDTA to the sample, you're able to see that those sort of bright punctate dots were removed. So again, yes, we were able to use EDTA in order to hopefully reduce the number of aggregates that we're getting in our samples. However, there is the backup issue that sometimes EDTA can cause a decrease in signal. So here is on the same sample, a different antibody that is also sitting with the same buffer. The addition of EDTA, you can see there was a great decrease in the signal of a good antibody. And so this just leads to some of the thoughts that you should
Make sure you know what antibodies are prone to having a decreasing signal due to EDTA, and this is not all antibodies. So when we're testing all of our antibodies together, what we'll do, we'll split up our antibodies into those that need EDTA because they're prone to aggregation, and we'll add EDTA to those buffers. And then we'll also look at the antibodies that are potentially decreasing in signal because of the addition to EDTA, and this isn't all antibodies, it's some antibodies. And we'll separate those into a separate group where their buffer doesn't have EDTA. And we'll make sure that these two stay separate when staining, so that way you're getting a decrease in aggregation in the antibodies that need it, and that you're getting, you're not losing signal in the antibodies that have it. So with that, that addresses some of the initial issues that we have, and if there are any questions, I'd love to answer those.
So are you doing sequential staining with your panel with EDTA and then your panel without EDTA?
Yeah, so in our most recent staining with GBM, we did add EDTA to address a couple of the antibodies that were aggregating, and so what we did was we split up our panels, and we had sort of two vials, one that had EDTA in it, one that didn't have EDTA into it, and we made sure those didn't overlap so that we didn't get decrease in staining in those antibodies that would be decreased due to EDTA.
So let me clarify on that point. So out of all the antibodies we've tested, I think we found 3 that are attenuated by EDTA. So, you know, the vast majority of the time, you should be able to use this as a single step. So it's not like as a routine practice, you shouldn't need to break things out into separate panels. You should try to keep it together as a single panel as much as you can. So that would be the first thing I would say. And the second thing is that we should put on, maybe we can put on the website because I don't think we put anywhere in the presentation the concentration of EDTA.
Yeah, there's a couple of questions more like protocol detailed.
Yeah.
Maybe Mark, is it in the protocol.io, like how to add the EDTA?
I don't know if we put that on there.
If not, we can upload
Yeah.
it, because there's some like more like, you know, what's the concentration, what step. I think it would be good if we had the actual staining protocol. I don't know, I haven't.
No, we don't have protocol.
I guess. I think it's 100 micromolar, isn't it?
1 minute.
1 millimolar? Yeah.
So I think, you know, it's a really nice tool. Vast majority of targets it doesn't affect, but if you've never checked, you should definitely look at with and without to make sure it doesn't kill the signal.
Okay, so we will post the protocol for people. There's a question here, you know, what steps of this antibody validation workflow that you guys talked about are broadly shared across all multiplex imaging platforms, and which of them are MIBI specific?
Overall, like visuals,
Like the codex, for example.
okay, I'm actually not too sure because I've only ever done MIBI, so I don't know.
I mean, I would say about everything they've covered so far, I think are in general, you could, you know, substitute in the phrase for whatever platform you're using, and it would probably equally apply. I mean, because all the platforms, you know, essentially the vast majority of them, you have primaries that are directly conjugated. And anytime you're conjugating a primary, you know, you always want to test it and you always want to make sure it's working after you've conjugated it. And you'll actually see that, you know, most antibodies, if for instance, the ones that might fail after conjugation, it's usually not specific to putting in a metal tag. It's just covalently modifying the antibody in general. So, you know, so these kind of failures can typically happen anytime, can happen whenever you're modifying the primary. So I think most of that's generalizable. I know from talking to people in Gary's lab that do codecs, they also have issues with aggregates. Whether or not EDTA would help with those, I don't know, because we haven't ever tried any of that. So, but by and large, I think the workflow is kind of general for the most part.
Kind of to follow up on that, as far as like differences for if you're conjugating a new protein outside of thinking about what metals are already used in your panel, is there any consideration to what metals you choose to conjugate with what antibodies? For example, like with IF, you might choose a certain fluorophore because your protein has like abundant signal versus a different fluorophore if the signal is low, or does it not really matter because it doesn't matter which metal you choose?
So I think this is kind of addressed as we talk about some of the overlapping from one channel to another, but it is
Okay.
possible that you have some like +1 where you might have an antibody at say like 141 and another antibody at 142. You might get some overlap from the 141 and the 142. So typically you wouldn't want to put a super, super bright antibody on 141 and then a super, super dim on 142 because you might like sort of overlap those two signals. So there is some consideration in how abundant or not abundant your antibody is in the fact that you might get a little bit of overlap. So there is some thought that is taken into consideration, but also we try our best to like deconvolve these things to the best of our ability, but you don't want to make it harder on yourself if you don't have to.
Thank you.
Do the aggregates show up on IHC, and can you talk a little bit more about how you actually identify that something is an aggregate and not just DIM or some other type of signal?
So yeah, I don't think we've seen too many of the aggregates in IHC necessarily. Mostly it comes around when we're doing MIBI. But the sort of way that we identify an aggregate versus not an aggregate is comparing to an IHC. So you should know what your signal is looking like. If you're expecting some sort of like diffuse membrane staining or some sort of like circular nuclear staining, and all of a sudden you're just seeing a lot of punctate dots. Like being aware of what your signal should look like off of IHC is a good way that if your MIBI staining is not looking like your IHC, that you might be getting aggregates. And again, it's normally you're seeing these really bright dots in very punctate areas where it wouldn't really biologically make a ton of sense to just have a ton of antibody in a really, really small area. And so, yeah, the comparison between an IHC and MIBI is a really good way of identifying an aggregate in that signal.
How do you tell the difference between a problem with the antibody, a problem with the conjugation, and a problem with the tissue that you're testing on?
That's that is a big question. It is unfortunately kind of a trial and error type process. I think Alea touched on this earlier. You can spend a lot of time figuring out exactly what the issue is. And we have had some antibodies where we have spent some time. And when it comes to this, there is no sort of right answer or good really way of knowing where the issue really stands. You kind of have to go through and think about where each issue might be and address it in that way. So if it happens to be the antibody and the conjugation, then maybe you'll see it when you look at your metal loading. If it happens to be a tissue and you try staining a different tissue and it's working on that tissue, then potentially with the tissue. If you order another clone of an antibody and all of a sudden it's working, it might have been the antibody itself. So there's not really a solid one answer fits all on how the issue can be addressed. You kind of have to work these things one step at a time and find where the problem is.
I think just to add to what Ben said there, I think, that this is where the importance of before you even get into testing the antibodies, if you have well-vetted tissue controls and you have tissue microarrays comprised from multiple tissue blocks, it doesn't completely eliminate the possibility that the tissues are the problem, but it makes it less likely that that's the issue. And then I think in terms of teasing out, if it's an issue with the antibody or with the conjugation, the lowest, at a very minimum, right, an antibody when it comes from the vendor, you should be able to have it work with standard chromogenic IHC, right? And if you can't, and you feel confident in your tissues, then it's the antibody, right? So I think, and that's why, the steps that Ben kind of laid out here of comparing an unconjugated and a modified antibody are really important because it allows you to kind of tease those two things out.
What about antibody isotype, so IgG versus IgM, and do we only use monoclonal or polyclonal is also fair game?
So as far as monoclonal and polyclonal, we've used all of the above. Sometimes we'll test those things next to each other to see how the monoclonal does versus the polyclonal. As far as I know, I think we only use IgG. I don't think I've ever seen anybody using anything else.
IgM can work, but it's an avidity versus affinity thing. And so when you do the standard commercial chemistry with reduction and alkylation on the IgM is a pentamer and it falls apart. And so you can sometimes not get binding anymore, though I do know of IgM clones that have worked post-conjugation, but you should be cautious. I would definitely, IgGs are preferable in general. That's the main isotype to work with.
Can we change the conjugation protocol to make the IgM?
There are definitely alternative conjugation protocols. There's one out there. I think it's linked off the INPATH site, but also it's kind of out. I think we have a protocol IO for it too, where you use an amine reactive intermediate and do a reduction step. So the IgM can stay intact that way too. Yeah. So there are alternative chemistries, but you have to go one step away at least from a lot of what is commercially available out there.
So we had a phone a friend from the Nolan lab. They said that a lot of the conjugation process is now quite similar on Codex for MIBI. And so you now thought that anything that makes it fail on Codex, it will probably also fail for MIBI, and that he didn't think EDTA would be as helpful for the Codex related issues as it is for us. So thank you. What's the optimal mass range on the new commercial instruments?
Is it starting somewhere in like 39 to 1?
So I think up to 200.
Up to 200? Yeah. So yeah, it's the mass range.
Cool. All right, well, thank you, Ben. Okay, so we're gonna take our break now. We started a little late, so we'll come back a little bit late, and we'll resume at 10:20.